Hey there. If you just took the 2026 AP Physics 1 exam and you have kind of been going over question 1 in your head, wondering if you got it right, let's just figure it out together. I'll go through every part and show you where the points actually are. And hey, if you are here to get a head start on an exam that's still coming up, stick around because this one is a great example to learn from. Ever since they redesigned the exam format back in 2025, the exam follows the same four question types every time in the same order. So, question one is always what they call the mathematical routine question. It's the one where you sketch a graph, derive a formula, and then explain your reasoning. Let's look at the problem statement here. Water is coming out of the nozzle of a fountain, and the launch angle is given as theta 0, and the initial velocity is v0, and then it goes like a projectile, reaches a maximum height, which is h1, and the maximum height is at this point, and then it comes back down and then reaches the same level as the launch point in time tf. As I explained before, this is a mathematical routine problem. So what does that mean? We have three things to do here. The first thing is we have to make representations. In this problem, they're expecting us to make velocity versus time graph, which is for both horizontal velocity and the vertical velocity. How is those components changing with time from time 0 and then the final time tf? So how is the velocity changing? And then we come to the derivation part. So that's where we have to derive an expression for the exit speed v0, which is the speed right here at the launch point. And then in part A3, we have to also derive an expression for the volume flow rate, Q. That is a fluid part of the question. A2 is actually kinematics part. And then we come to the third thing we have to do in this problem, which is in part B, to make a claim, and you have to defend it with reasoning based on physical concepts. The question is asking us what is going to happen to the maximum height the droplet is going to travel if you keep the amount of water that is coming out of the fountain same. That means the volume flow rate is the same and they're going to decrease the radius. So how is that going to affect the maximum height before it comes back down? Is it going to increase, decrease, or stay the same? So that's what we have to justify with the reasoning. Let's move on to part A1, where we have to draw the graphs, the horizontal velocity and the vertical velocity, and how it changes from 0 to TF. So before we do the graph, let's see what are the directions of the velocity components. We know that the initial velocity is v0 at the angle, so the two components should be, the horizontal component should be to the right side, and the theta 0 is the angle. So the horizontal component should be v0 cos theta 0. And then the vertical component should be v0 sine theta 0. So those are the two velocities. And we are going to see how those velocities are changing with time. So first, let's look at horizontal velocity. So to understand how the velocity is changing, we know that the thing that affect the velocity change is the acceleration. So do we have any acceleration in the horizontal direction? For an acceleration, we need a force. The question does not talk about any air resistance in the horizontal direction. So in general, for any projectile motion, we assume that unless it's specified, we assume that there is no acceleration in the horizontal direction. So if there is no acceleration, that means the horizontal velocity should be a constant throughout. It does not change. So this is a horizontal velocity at the beginning, v0 cos theta 0, and that will be constant throughout from 0 to tf. The velocity is not changing. That means it's constant throughout. So the graph is going to be a straight line all the way to tf. Now in the vertical direction, we see that the initial velocity component in the vertical direction is v0 sine theta 0. And we know that there is a force acting on every projectile. In this case, it's a water droplet, which is the force of gravity acting down all the time. So when you have a force of gravity acting down, we know that there's an acceleration due to that, which is, we call it the acceleration due to gravity, which is g in the downward direction. So the velocity at the starting point is in the upward direction, and the acceleration is in the downward direction. They are against each other. So when they are against each other, the velocity is going to be decreased. That's why it keeps going up until it reaches a maximum height where the velocity in the vertical direction becomes 0, and then it starts to go down. So let's start from the initial velocity, which is v0 sine theta 0 here. And then at the highest point, the question is saying that the total time taken for the water droplet to come back to the same level is TF. So the time taken to go to the maximum height, which is only half of that motion, will be half of the time, which is TF over 2. So that is a half of the time. At that point, the water droplet is at the highest point. So it starts from the maximum velocity, and then we said the acceleration due to gravity is in the downward direction. So the velocity will be decreasing linearly because that acceleration is a constant. So when the acceleration is constant, the velocity should be decreasing or changing linearly. In this case, it's decreasing linearly. So this is a maximum height point. That's where the velocity in the vertical direction becomes 0. And there is still that acceleration due to gravity acting down. So the velocity keep on increasing in the negative direction now. So the velocity is 0 at the top, and then it keeps on increasing in the negative direction until it reaches the same velocity as the initial velocity, but in the negative direction, because it reaches the same height as it was launched. So this is a final point at TF, that is the final velocity, and it'll keep on going in the same line until it reaches that point. So that is the final point when the water droplet reaches the same height. The details graders are looking for in part A1. For horizontal velocity, there are two things. One is it a flat line? Is it a flat horizontal line from time 0 to TF? And then also, if you look at the problem statement, it's showing that the upward direction is taken as positive, and to the right side is also positive. So those are the positive directions. Now we see that the horizontal velocity is to the right side. So that should be a positive value, which is in this case, it should be V0 cos theta 0. So that positive value will be same throughout. So you should be drawing a flat horizontal line like that. So you got the point if you did that. And then for the vertical velocity, again, you have to show a positive value at the starting point because the initial velocity in the vertical direction is in the upward direction. So that is a positive direction. So that should be a positive value. So I'm showing positive V0 sine theta 0 as the initial point. And then after that, are you showing a straight line but not horizontal? It's going straight down because the velocity is changing, and it's changing linearly at the same rate throughout. So because it's the rate is same as the acceleration, which is g in the downward direction. So it's constant throughout. So you should be showing a straight line with the same slope throughout from 0 to TF. So there should not be any change in slope throughout. So it'd be a straight line. And then also they're looking for at the highest point, we know that the velocity in the vertical direction becomes 0, and the highest point happens at the halfway mark for the time. So it's 1/2 TF. So 1/2 TF is the velocity becoming 0. And then it keeps on decreasing. So it's a straight line going down. And then at the end, at TF, the droplet is reaching the same height as the launch point. So that means the velocity should be the same in the vertical direction, but in the negative direction, in the opposite direction. Now let's move on to part A2, where we have to derive an expression for the speed V0. And remember that V0 is the speed at which the water droplet is coming out of the nozzle. And in the expression, you can only have these variables in it. You can have theta 0, which is the launch angle, and h1, and any physical constant such as g. So this part of the problem can be done two ways. You can either use kinematics equations, or you can use energy method. It does not matter which method you use. You'll be getting 4 points if you did the method correctly. So I'm going to show the kinematics method first. And before that, the problem clearly says that you have to start with a fundamental physical principle or equation for these kind of questions. So you have to clearly say, in this case, if you're using kinematics method, we have to clearly say which kinematic equation are we using. So first of all, let's look at the different options we have. The kinematic equations we have is V equals V0 plus AT, and then we have V square equals to v0 square plus 2 times acceleration times the displacement delta x, and then delta x equals to v0 times time plus 1/2 of acceleration times t squared. So we have three equations, three options. The first thing is which one should we select. So we are trying to derive an equation for v0, and interestingly, all the three equation has v0 in it. So you can um, technically use any of the three equations, right? But the catch here is if you look at the problem statement, it clearly says that you should be only having theta 0, h1, and g in the final expression. So that means we cannot have time in the final expression. So if you use the first equation or the last equation, you can see there is t in it. So the final expression will be having the time in it, which we cannot have in this problem. So for that reason, we should be selecting this kinematic equation, and you have to write that as the first sentence when you solve this problem. So that is the first part. We write the equation v square equals to v0 square plus 2 times a times delta x. That is the equation we'll be using. So let's start with that, v square, and then we will be doing this in the y direction because we don't know how much it travels in the x direction. What we know is how much it travels in the y direction for the maximum displacement. So I'm going to use that equation in the y direction, v0 square plus 2 times a times delta x. Let's put x now, and then we can substitute later. Another thing is the projectile motion for the water droplet is like that. Should we use the whole travel of the water droplet? We cannot. The reason is we said we are going to use this equation in the y direction, and the displacement delta x, if you take the first point and the last point, there is no displacement because there is no change in or height difference between those 2 points. So this equation does not give us anything if we use this as a starting point and this as an ending point. What we can do is we know the starting point right here, and then we only consider the first half of the motion. We know that in that case, if the starting point right here, the ending point is at the top, the displacement is given as h1, and we can have that in the final answer. So we are only going to look at the first half of the motion, and that will give us the initial velocity. So the final velocity at the top, that's another thing. When the water droplet reaches the highest point, the final velocity in the vertical direction is 0. So we are using this equation in the y direction. So in the y direction, the final velocity is 0. So 0 square is again 0. And the initial velocity, remember that initial velocity was v0 sine theta. So when you square that, you will be getting v0 square sine square theta plus 2 times the acceleration in the y direction is, it's not g, it is negative g because it's in the downward direction. So times negative g, and the displacement now, displacement is upward direction, that is positive. So you can write h1 here. Now the only thing is we can simplify this. This whole term is negative, so you can move that to one side. So the equation becomes v0 square sine square theta 2 times g times h1. Then you can take a square root to remove that square. So you'll be having v0 sine theta equals square root of 2gh1. And then you simply divide both sides by sine theta. So it'll be square root of 2gh1 over sine theta. And that is our expression for v0. And then you can double check if we are only having theta 0. One thing I forgot is these are theta 0. So we have theta 0 in the equation expression, h1, and physical constant. G is a physical constant, so that is fine. So the expression he got is correct here. Now let's see how we can solve this using energy method. When I say energy method, what we're going to be using here is conservation of mechanical energy. So for the fundamental physical principle, as a first sentence, you have to write conservation of mechanical energy. So that is where we are starting from. And energy conservation we can apply at the starting point and the highest point. We take those 2 points and we apply energy conservation. So we know that at the starting point, the velocity is, it's not v0 sine theta or v0 cos theta, it is the v0, that is the actual velocity. Because remember, when we are using energy method, energy is a scalar, so we are not looking at the components or different directions. We need the actual velocity or the actual energy at that point. So for the kinetic energy at the bottom, we'll be using 1 half times m. Now m is the mass of a single water droplet. It does not matter what size it is, because you're going to see that the mass is not going to be a factor here. So we'll take a small water droplet with mass of m, and then the velocity is v0, the actual velocity at the launch. So that is the initial energy, and we don't have any potential energy if we take that as our reference line for potential energy. So that is the energy at the bottom, and then we compare that to the energy at the top, and then we set them equal to each other. Because of energy conservation, we ignore all the energy loss because of air resistance or other factors. So at the top, what we have is the gravitational potential energy, because there's a height h1 from our reference line. So we're going to have mg h1 is the gravitational potential energy. And that is not the only energy there, because remember, only the vertical velocity component becomes zero. There is a horizontal component of the velocity all the time throughout the travel, which is v0 cos theta. It is a constant. That's why when we draw that graph for the horizontal velocity, it was a flat line, horizontal line, because it does not change. So that velocity is there. That means there is a kinetic energy at that point, which is 1 half times m in place of velocity. The only velocity there is v0 cos theta, so v0 square and then cos square theta, because we square the velocity there. And now we can, first of all, we can see the mass is not a factor, because you can cancel the mass from all the terms. And then we are trying to find an expression for v0. So we are going to combine the v0s together. So I'm going to move this whole term to the other side. So on the left side, I have 1 half times v0 square, and then minus 1 half v0 square cos square theta, and equals to m is gone, so that is not there. So we have g times h1, and we can factor these together. 1 half v0 square is common, so we can factor that out. So 1 half v0 square times, we have 1 from here, and then minus cos square theta equals to gh1. Now from trigonometry, we know that 1 minus cos square theta is sine square theta. So we have 1 half v0 square sine square theta equals gh1, and then we can multiply 2 on both sides. So we get v0 square sine square theta equals 2gh, and then you take a square root on both sides, and then you divide by sine theta. So the final answer, once you solve it, you'll be getting v0 equals square root of 2gh1 divided by sine theta. You can see that it is the same expression even when we use kinematics or energy method, does not matter. So in this problem, the method does not matter. The thing is, when you start with the fundamental physical principle, you have to specify, are you using a kinematic equation or are you using energy conservation? We have to specify that in the beginning. When we do this process, we will be getting the same answer. So that is our part A2. Now let's move on to part A3. In this part, we have to derive an expression for the volume flow rate. First, we have to start with the fundamental physical principle or the equation, and that equation is nothing but the definition for the volume flow rate. So the volume flow rate, so you can start with volume flow rate Q is equal to the area of cross section of the nozzle, because the water is coming out of the nozzle here, times the velocity of the water coming out. And remember, we calculated the velocity of the water coming out in part A2. So this problem is actually testing you if you can connect what you found in the previous part to the next part. So let's start with that equation we found in part A2. The equation for V0, the velocity, is square root of 2g times h1 divided by sine theta 0. And also the nozzle is circular and they're giving us a radius, so we know the area of a circle. You can simply find it using the pi r square equation with the radius is r0, so pi r square 0. And then now the only thing is you combine them. Volume flow rate is area times the velocity. Area is pi times r0 square times the velocity you got in part A2, which is square root of 2gh1 divided by sine theta 0. So that is our answer. And then you can also check if it's only having the variables allowed in this expression. So the expression can be having theta 0, which is right here, can have h1, r0, and physical constants, so we can have g in it. So this is the correct expression you find for the volume flow rate. One thing to add is if you got part A2 wrong, that means you got the velocity expression wrong, but you did the calculation for A3 correctly using the equation Q equals to AV, and then in place of the velocity, you substituted whatever velocity you got in A2, and then you did the process correctly for A3, you will still get the point for A3. It does not matter the expression you carried from A2 is wrong. And now we are moving on to the final part of the problem, part B, which is qualitative reasoning. For a mathematical routine problem for qualitative reasoning, you're not expected to use any mathematical equations in this part, because this is not a part where you're supposed to derive anything. You should be able to make a claim based on the problem, and then you should be able to justify your claim using your physics reasoning. Here, the nozzle is now replaced with a nozzle with smaller radius, and everything else is staying the same. The volume flow rate is the same from the fountain, and the launch angle is the same. So the only difference is the radius of the nozzle is getting smaller. And we have to make a claim on how is that going to affect the maximum height the water droplet can go. It was h1. Now with the new nozzle, that height is now h2, and we have to compare h2 with h1. This is how we can explain it logically. Since the volume flow rate is the same amount of water is trying to pass through a smaller radius nozzle. And that means the water has to flow out faster so that the same amount of water as before can exit the nozzle. So the speed of the water has to increase if the radius gets smaller. And if the speed gets greater, with the launch angle being the same, the vertical velocity component also has to be greater. And if you have a greater vertical velocity, it means a greater vertical displacement, which means the maximum height will be greater now. So here the claim has to be h2 greater than h1. For points, the grader is expecting two things here. The first thing is, are you making the correct claim that h2 is greater than h1? And the second one is, are you able to justify the claim based on reasoning like I just explained? So if you only got the claim part correct, you will be earning the point for that. And also if you did the reasoning part also correct, you will be getting the full points. So that's all from question 1. If you just took the exam, hopefully that gave you a clearer picture of how you did. And if you've got an exam coming up, here's what I really want you to take from this. Look at what this one question made us do. We sketched graphs, we derived expressions, and then we justified our claim step by step. If you want more of these, everything is over at physicsontrack.com. I am working through all 4 of the 2026 FRQ questions in order. Next one is question 2. Go ahead and subscribe to this channel so you don't miss it, and I'll see you in the next one.